In section 8.4, we're going to talk about integrals containing forms like these. The square root of a squared minus x squared, the square root of a squared minus plus x squared, and the square root of x squared minus a squared. Now, in order to do this, we're going to need to make a substitution that will eliminate the radical. And the type of substitution we're going to use is a trigonometric substitution. And the way that this works, let's take a look at example 1. Notice that we have the form 4 minus x squared in our denominator here. And if you recall, if we were to set up a right triangle with sides of a side of length x and a hypotenuse of length 2, using trigonometry, well, first of all, the Pythagorean theorem, we would get that the other leg of the right triangle would have a length square root of 4 minus x squared. Now, labeling this angle theta, we would see that the sine of theta is x over 2, or solving for x, we would see that x is equal to 2 sine theta. Now, this is going to be the substitution that we're going to use, and you'll see in a moment why it works out so well. So let's go ahead and set up our integral. So we have the integral of dx over x squared square root of 4 minus x squared. And we're going to use the substitution x equals 2 sine of theta. Okay, now we're going to need to replace dx. So let's figure out what dx is. So the derivative of 2 sine of theta is 2 cosine theta d theta. And now let's plug in. So instead of dx, we have 2 cosine theta d theta. Instead of x squared, we have 4 sine squared of theta. And instead of the square root of 4 minus x squared, we have the square root of 4 minus 4 sine squared theta. Okay, so let's simplify as much as we can here. For example, under the radical, I see that I have a factor of 4, so I'm going to go ahead and pull that out. So we have 2 cosine of theta d theta over 4 sine squared theta times the square root of 4 times 1 minus sine squared theta. Okay, now 4 obviously is a square root. We can take the square root of that. 1 minus sine squared theta is the same as cosine squared theta. So simplifying, we have 2 cosine of theta d theta over 4 sine squared theta times the square root of 4 is 2, the square root of cosine squared is cosine of theta. Now, actually it's the absolute value of the cosine of theta, but I'll explain in a minute what restrictions we're going to have to place on x and theta in order to avoid having to worry about that. Alright, so we're going to have equals the integral of, now the cosine of thetas are going to cancel as well as the 2's. So coming back over here, we're going to have d theta over 4 sine squared theta which is 1/4 the integral of cosecant squared of theta d theta. And the antiderivative of cosecant squared, remember, is cotangent. Actually, negative cotangent. So that's going to be negative 1/4 cotangent of theta plus c. Alright, so here we've done our first trigonometric substitution. Now, this is the mechanics of the problem. One thing we want to keep in mind is, again, we're going to have to place some restrictions on theta. In particular, when we're using this substitution, 2 cosine theta d theta, which we're going to do when we have the form a squared minus x squared, we're going to want to place a restriction of, well, actually I said that wrong. Really the substitution we're using is 2 sine of theta. And in that case we're going to want to place the restriction of on the sine, the theta values to be between negative pi over 2 and pi over 2. So here we're restricting theta to negative pi over 2 to pi over 2. Now, one reason that we're doing this is if we wanted to solve for theta in this equation, we would have to say that x over 2 equals sine of theta, and we would say theta is equal to the inverse sine of x over 2. And so we want to be able to have theta be in the range of the inverse sine function. Another reason we're doing that is, remember, the range of the inverse sine function covers all of the possible sine values from negative 1 to 1. In this case then, if we take theta to be between negative pi over 2 and pi over 2, then our x value will be between 2 times negative 1 and 2 times 1, which is anywhere from negative 2 to 2. Now, why is that important? Well, first let me write that down. X is going to be between negative 2 and 2 in this case, and that's important because of the domain of the function we're integrating. In fact, if you check values here, all of the x values have to be between negative 2 and 2. There's another restriction, of course, because of the natural domain of this function. X cannot be 0, and it can't actually equal 2 or negative 2. But in any case, all of the values are covered for x that we would need. They all are in this interval. So now let's look at a list of restrictions and which substitutions we use for which expression. This list is table 8.4.1 in your Anton textbook.